slides.
Of different slides? Oh,
Yeah.
we see, in your thing, we see the previous slide as well.
Oh, okay.
Yeah.
Know how to do that. This happened before, actually. Let's see, is there an option in sharing? It's a PowerPoint sort of a.
Ways to share screen rather than
Hang
share
on, hang on.
window.
This one. Not both. This better?
Yep.
Okay.
Good.
Okay.
Yeah.
Wait, but why am I?
Yeah, but it's not Mike's talk, I believe.
My talk's at 1.
Yeah. You should read. Mike's talk is is the second talk in the series. Okay, so today is a double header. We have so I'm going to introduce the first talk, and I will give you the preview of the second talk. Alan Dorsey is here from Georgia, and he'll talk about hydrodynamics of supersolids. I think I've known Alan since, oh God, 20. When I was a grad student, he did I first became aware of his work on quantum Hall pneumatics with Leonard Zhovsky, and it looked like a piece of magic, and it still feels like a piece of magic that Alan and I periodically talk about going back to. And today he's going to talk about things that are, I guess, not controversial anymore.
We'll see.
Supersolids, nobody.
We'll see.
We'll see. All right. Try to make it. Anyway, unfortunately, he's leaving today. He'll be around until 3. So if you want to catch, and maybe we'll try to bring him back next year or next semester. I don't know. So he seems to be open to visiting. So without further ado, how do I get rid of that?
And the ... I for the meeting here.
Sorry, I didn't realize that it's actually showing up everywhere. Do you know how to do this?
The thing labeled more.
Yeah, but it's not on it's not on this screen.
Look behind you. It might be down here.
Oh, I see. It's
Oh, I
no,
see.
it's an extend thing. So if I go to ... what do I do?
Hide
Disable.
floating meeting controls. Hide floating.
Oh, thank you. All right, and that's a good segue. Mike Koladrubitz will be giving talk after lunch. What did I say? 12:45, I think. So those of you on Zoom, first you're going to miss lunch, and second, you should come back at 12:45 for Mike. Okay. All right, Alan, sorry.
Thanks. Happy to be here today. Actually went to a comedy club last night since we didn't have the group dinner. So I feel like I should be doing some crowd work as well for the people that are closest to me, but I won't do that. So I'm going to talk about hydrodynamics of supersolids, and this is work that I've done off and on for the last 15 years. It's become more topical within the last couple of years because of some new experiments on cold dipolar gases, in which the experimentalists claim to have observed hints of a supersolid phase, and as well vortices in this putative supersolid phase. So I'll kind of go through the history of supersolids. Now, some of you have seen versions of this talk before, and so for that I would apologize for some of you that may be new, but feel free to ask questions, which I probably can't answer. Work I've done off and on with John Toner, Paul Goldbart, and then some of my former PhD students, Chi-Hyuk Yu, Kinjal Das Biswas, and Vashik Aswamy as well. So let's see if I can get this. Advance.
Uh-oh, you got stuck altogether.
Okay, this will work.
Good.
All right, so kind of an outline. So I want to talk about the sort of the history of supersolidity and talk about what it is. And the basic question is, can Bose-Einstein condensation occur in a solid? And there's a long history to this that goes back almost 70 years. So I think the history itself is interesting. So I'll give you a brief history of superfluids and supersolids. And then also talk about if this putative supersolid phase did exist, how would we know it? What are the observables that would allow us to detect the supersolid phase? And then I'll talk a bit about supersolidity and dipolar gases, dipolar condensates. And then I'll go on to talk about hydrodynamics. I'll talk about mode counting, which is something I talked about in Shriram's class earlier this week. And a variational approach or Lagrangian approach to supersolid hydrodynamics, and then finally vortex dynamics in a supersolid. So the question is, can Bose-Einstein condensation occur in a solid? I realize now that BEC has different interpretations, so we also have the bulk edge correspondence, which might be relevant at some point.
Yes, you.
Oh, use the pointer.
Yeah, I know. Options sometimes.
Good. Can Bose-Einstein condensation occur in a solid? We know that Bose-Einstein condensation exists in a gas phase with cold atomic gases, and in liquid phases, and in liquid helium-4 at low temperatures, but can it also occur in a solid? And so, phrased differently, can off-diagonal long-range order, which is another way of kind of framing Bose condensation, coexist simultaneously with shear rigidity? So broken translational order in a solid. And I would say in the 1950s, the idea, when there was a lot of work, active work on kind of understanding Bose-Einstein condensation, superfluidity, the answer to this question was no, that Bose-Einstein condensation really requires that the bosons in the condensate have these extended wave functions which overlap, and that this doesn't happen in a solid where you would have very localized kind of Bonnier type states in a solid. So it would seem that Bose-Einstein condensation probably couldn't exist in a solid where we have localized wave functions. But but maybe there's more to the story. So that's the history. The history really goes back to a fundamental paper by Penrose and Onsager in 1956. And so, as I said, this is almost 70 years ago. And what Penrose and Onsager concluded is that one could not have Bose-Einstein condensation in a solid. And I think you all probably know Lars Onsager. This is Oliver Penrose, who is the older brother of Roger Penrose. So he made a lot of important contributions to theoretical physics in his own right. So Penrose and Onsager were studying kind of the fundamentals of Bose-Einstein condensation and applications to really to superfluidity in helium-4. But you can see that in the introduction to their paper, they state very clearly, conversely, it is shown why one would not expect Bose-Einstein condensation in a solid. And so they claim to have, in a sense, proven in this paper that one could not have Bose-Einstein condensation in a system with broken translational symmetry and crystalline order. But there's more to the story. In 1970, so 14 years later, there was another nice piece of theoretical physics by Jeffrey Chester at Cornell University. And what Chester said is, yes, what Penrose and Onsager did is all fine and well. But what Penrose and Onsager didn't allow for is the possibility that the solid might have some defects in it. And so the question is, once one allows for some defects in the solid, by defects, what I mean are vacancies in the solid. And a vacancy, just to describe this, is essentially you have your solid with periodic crystalline order, and a vacancy is produced when I go in and imagine plucking out a particle from one of those sites. So that creates a vacancy. Alternatively, I can put in interstitial atom where I take an atom, the same species, and I put it into some interstitial site between two atoms in the solid. So the work by Penrose and Onsager assumed one had a regular periodic lattice with no vacancies and no interstitials. And what Chester pointed out is there might be a situation where if you allow from some of these vacancies and interstitials, you might then have the possibility of Bose-Einstein condensation. And you can see how, yes.
What is the density of those impurities or like vacancies that you have to have for this to happen?
Yeah, well, this particular work, the proof in principle that one could have crystalline order with vacancies and Bose-Einstein condensation, there's kind of a nice result, which I won't go into very much, which if you write down a variational wave function for the many boson system, which is localized, you can map that onto some effective problem in statistical physics for a collection of interacting particles. And in that effective classical system, if you lower the temperature, then eventually for most kinds of interparticle interactions, it will freeze into a solid phase. But at any non-zero temperature, that solid will have some dilute concentration of vacancies, where the vacancy concentration will be governed by the energetics for a vacancy. So just so we get to your question, the number kind of depends on the temperature and specifics of the solid, but there is a nice way to kind of map this, which was kind of a key insight in Chester's paper. And so one of Chester's conclusions is that a quantum crystal can only have Bose-Einstein condensate if it has a finite fraction of vacancies. So essentially what he's saying is, okay, the Penrose-Onsager result is no longer applicable once we have a finite fraction of vacancies, and maybe in that circumstance we have Bose-Einstein condensation. And this is just another cartoon to kind of explain what vacancies and interstitials do in a solid. So if you think about how to locally change the density in a solid, you can do that in two different ways. One of which is you can, as shown above here, you can locally create a density fluctuation by just expanding or compressing the lattice without changing the number of particles. But you could also imagine changing the density locally by putting in vacancies or interstitials. So here we have a lattice with there's a vacancy here, that's site, and we have an interstitial here. That also changes the density locally. And in general, the changes in the density will be a combination of these local changes in the lattice displacement, along with changes in the density of vacancies and interstitials. In a classical solid, the density of these vacancies is temperature dependent. It is governed by some Arrhenius factor, where E sub V is the energy required to create a vacancy in the solid. And one question is, okay, in a quantum solid, can one have 0 point vacancies? So vacancies they're not due to thermal fluctuations, but for instance, through some quantum fluctuations.
Are you going to write an order parameter for vacancy density? Is there a way to define vacancy density sharply? Like, I just want to measure, give me a wave function, I'll measure the vacancy density.
Probably not sharply.
Right, I think that's an issue.
So
Like, I would take an issue with like these questions. Like,
Yeah.
there's no operator. Once we talk about quantum problems, there should be an observable.
well, there probably is an observable. Let's revisit that question.
Sure.
Uh,
Can I ask a remedial question?
Please, yeah,
So if we just start with the free boson gas,
yes,
then we find Bose-Einstein condensate.
yes,
Then you start adding interactions, and then the claim is once the interactions become sufficiently strong so that it's like a solid, then that solution goes away. This is, I'm supposed to understand the absence of the.
Yeah, I mean, sort of. So I think a key insight was this paper that was published at about the same time as the work by Chester, by Andreev and Lifshitz, which provided a description of a supersolid, although they don't call it that in this particular paper. So this is Andreev Lifshitz, 1969. And they again refer to the possibility of there being vacancies in the ground state of a quantum crystal. And it's imagined that those vacancies are dilute in some sense, but the vacancies themselves, since they're the absence of a Bose particle, you can think of those, they're also bosons. And the rough idea is those vacancies can form a fluid, which itself Bose condense. So the Andreev Lifshitz picture, roughly speaking, is you get a superfluid, if you like, of vacancies that exist in the ground state of this quantum crystal, and that then they're delocalized and they sort of suffuse the whole crystal. So I'm sure that's a sharp.
I was asking you a more basic question.
Yeah.
If I'm just, I just write down the Hamiltonian.
Yep.
I want to solve it. And the problem is if the interactions are not weak, I can't really solve it. But if, suppose I could, is there like, is there some phase trend? Is there just a trend, some sharp transition when the interaction strength is some particular value, or? I'm not sure how I'm supposed to.
Actually, can I try to sharpen up his question?
Sure.
Let's for now stick with bosons, but keep in mind that for fermions, the answers is yes, 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 yes.
Okay.
At least some fermions. You know, if you start in the BEC and you crank up interactions, and by interactions right now, we're not saying which interactions. In principle, there are Yukawa interactions or there's some dipolar interactions, and they may all have different properties. The question is that you have an autoparameter for the crystal, which is periodic density modulation.
Correct.
And for the superfluid, you have this, you know, unsug or whatever, off diagonal. Let's stay in the superfluid phase. Let's imagine that you keep seeing the superfluid stiffness. It seems to me that if I play around with my Hamiltonian and I find interactions that make the superfluid order modulated in space, density modulations are going to have to come in. And it'll, from the point of view of long range periodic modulations of density, which is a hallmark of a crystal, I will have to say, oh, I have a superfluid that's modulated, and hence it has density modulation. So that's a coexistence. Would you call that a supersolid? Because in fermion systems, coexistence of charge density wave and superconductivity is not controversial.
Right.
So I feel like density modulations and superfluidity they can coexist in principle. It seems to me like as an complete outsider to this field, it seemed to me the controversy here was that they started in a crystal that was, you know, non-quantum at all. And so like actually building up, like the route that Vladimir is asking is kind of like the route where, at least to me, that's where there's no, the answer yes, that these things can coexist. It's not difficult.
Okay,
But
so
anyway, that's, I just wanted to like, you know, like, if we focus on order parameters, then having a modulated superfluid is an interesting question, which is not out.
right. So yes, in principle, the superfluid order parameter will be modulated. One tends not to worry too much about that. We have we look at basically the Q=0 mode, if you like, of that system.
But if it's modulated, you agree with me that if it's modulated in space,
Yes.
density being a scalar, you are going to induce density modulations.
Yes,
twice.
and in fact, so I'll briefly talk about a Landau theory for this supersolid phase that I had developed with John Toner and Paul Goldbart, in which we have to worry about coupling the superfluid order parameter with the goldstone modes of the lattice, so that there is some residual component of the solidity there, which is just the long wavelength phonons in the lattice, and when it in principle has to couple those two together. But there are some subtleties about how one defines this, and I'm going to evade most of those.
Okay.
So how do you look for this super solidity? And one very clever suggestion was put forward by Tony Leggett in 1970, where Tony proposed that one should look for what he called non-classical rotational inertia. So NCRI for short. And the idea there is, and it's kind of sort of inspired by experiments in superfluid helium. These are the Androshkovili experiments, torsional oscillator measurements, where you look at the moment of inertia of a fluid, a superfluid, you rotate it back and forth, and you find that when you go from the normal fluid phase into the superfluid phase, the superfluid component decouples, and one sees a reduction in the moment of inertia for the oscillator. And Tony proposed doing the same thing for a supersolid. I mean, roughly the idea would be taking a solid, rotating it. You change some parameter, temperature would be a natural one. So you start at high temperature where it's a normal solid, you'd have a classical moment of inertia, just calculate from the mass distribution of the solid inside your torsional cell. You lower the temperature, and if you then fall into this supersolid phase, his idea was that a portion of the solid, the superfluid component, would decouple from the oscillatory motion, the rotational motion. So you'd see a presumably abrupt change or reduction in the moment of inertia. And that's what he would refer to as non-classical rotational inertia. And he also put some bounds on that for an inhomogeneous system. So actually a very nice piece of work that's kind of stood the test of time. So I want to talk briefly about helium superfluid or supersolid helium, solid helium, just because it'll be important for some of the experiments we'll talk about in a minute. So helium-4 is a good example of soft matter. It's formed at low temperatures. So here's the phase diagram for helium-4. This is the lambda transition from the normal liquid into the superfluid. But as you pressurize helium, you can induce it to form a solid phase at a pressure of around 25 atmospheres. So you pressurize it and you go into this HCP phase for the solid helium. So it's these trivial, the experiments I'll talk about are, if you think about it, are highly non-trivial, because you have to do two things. You have to work at very low temperatures, and mostly at temperatures below 1 Kelvin, but you also have to work at high pressures. And so inside a pressure cell, because you have to get up to 25 atmospheres or greater inside this pressure cell. So the helium-4, it's a quantum solid. It has in the literature of quantum solids, there's a parameter that's called the de Boer parameter, which in some sense is supposed to be a measure of the quantumness of the solid. And the de Boer parameter is the ratio of the thermal Debye wavelength for the particles in that solid, divided by the sort of range of the interaction, which is sigma. So that ratio for helium-4 is about 0.3. For another noble gas, so solid argon, it would have a de Boer parameter of about 0.02. So the point is that not surprisingly, because helium is so light, it is the most quantum of those noble gases. It also has fairly weak interactions, and so it's a good candidate for any kind of interesting phenomena you might observe in a quantum solid.
So in the space diagram, the solid part, so the superfluid part, the transition is controlled by this Debye parameter. So,
Well, here the transition is controlled by well, you're pressurizing, you're pushing the atoms closer together. Right. It's a little sliver of BCC, but it's mostly HC.
but then on the y-axis, the temperature should be a function of Debye parameter. Because the more quantum
Oh.
it is, the more extent of superfluidity.
Yes, that's right, correct.
But it doesn't extend in that direction, controlled by the Debye parameter.
Sorry, I missed what lambda and sigma are, but that's,
So, yeah, so lambda is the thermal de Broglie wavelength,
all right. One of root T.
and one over T, right? And sigma is kind of the hardcore radius, effective hardcore radius of a helium atom. Just taking whatever potential you want to put in there for the helium interaction. So it's a figure of merit that gives you some idea of how quantum the solid happens to be. And here are the experiments that were reported back in 2004. So this goes back 20 years now. So you can see the long history here, from 1956. Now we're up to 2004. There were results reported out by Kim and Chan in 2004, where they took this idea of using non-classical rotational inertia, the thing that was proposed by Tony Leggett as a diagnostic for the supersolid phase, and they kind of took that to heart, and they did fairly careful measurements, difficult measurements on solid helium. And here is their torsion cell. So it's you can see here, this is actually a figure from the New York Times. So this is actually reported out in the New York Times. And so this doesn't happen very often, where there's a new experiment in physics, especially in condensed matter physics, low temperature physics, that's reported out in the New York Times. And the advantage of that is the New York Times could have all their graphic artists kind of engaged and make this great graphic. Where they have, here's a figure of the torsion cell. So there's a torsion rod, the helium's inside the cell right here. These two paddles on the side are used to excite and oscillate the solid back and forth. This is their cartoon. This is the Times cartoon of the helium-4 solid lattice, HDP lattice. And then this is the cartoon of the non-classical rotational inertia, whereas the idea was that a portion of the helium atoms were suddenly decoupling from the rotational motion. So there were a series of papers, series of results reported out starting in 2004 by the Penn State group, led by Moses Chan, in different geometries and so on. The effect, the non-classical rotational inertia fraction was very small, but it was detected. And then the results were subsequently replicated by a number of other groups around the world, at both Cornell, so John Reppy at Cornell, some folks at Rutgers and Japan, Korea, and so on. So there's a lot of excitement. At least some of us got excited by this and jumped on to try to figure out what was going on. This is the data. I don't want to go into, I don't really have time to go into this in much detail. So you fill the torsion cell with helium, then it gets pressurized, and then you do this measurement and you look at to look at the possible changes in the moment of inertia. You look at period shifts in the torsional oscillator, since the period of the natural period of the oscillator will be governed by the moment of inertia. So you're trying to detect very small shifts in the resonant frequency of this oscillator, and it's this is the plot. So as a function of temperature, you can see that there was something at a temperature that was associated with the supersolid the normal solid to super solid transition temperature, there was a sudden drop in the period of the oscillator, and then that was the signal for super solidity in the helium. I'm gonna just talk about this for a few minutes. So when the results came out, I started thinking about this with some of my colleagues. There are lots of groups that have attacked this in various ways, and I can see that Anatoly is on the call. He and a number of his colleagues have done some beautiful work on numerical work, sort of Monte Carlo simulations for this. I took a different phenomenological approach and just asked the question is, can we construct a Landau theory for the supersolid phase? And what would that look like? And the idea is it would look like the Landau theory for a superfluid. So here's our Landau free energy for a superfluid. We're assuming that the superfluid has the supersolid order parameter for the superfluid part has the same kind of U1 symmetry as one would expect for a garden variety superfluid. And so psi here is a complex order parameter. Our Landau, the coarse-grained Landau free energy has the gradient terms, the quadratic term, the coefficient of which changes sign at the transition, and then the quartic term to stabilize that. So this is the, if you like, the Mexican hat potential that you're all familiar with. If it were just a superfluid, then we would do the usual things. If we want to look at the critical properties, we would average over fluctuations. And we would find all kinds of interesting phenomena, various anomalies in specific heat and so on. But this would be for a superfluid. For a supersolid, we have to add in the other Goldstone modes in the problem, which are the low energy modes from the solid phase. So we have to couple the superfluidity to the phonon modes in the solid. So there's a coupling here between the modules of the order parameter squared and the strain fields in the solid. And then one of the questions would be, well, how do these strain fields modify the nature of the transition, and what are some observable consequences? What we claimed is that there should be anomalies in the specific heat, just like for superfluid helium, but for the solid itself, that there would be another indicator of the transition to the supersolid phase, because the onset of the superfluid part would induce sort of singularities in the elastic moduli for the solid. And these could be detected in sound propagation measurements and so on. Those were never observed. Predicted but not observed. So yes.
Why this kind of coupling? I would imagine that if I look at the kinetic term,
Yeah.
I can replace this gradient of phi modulus squared.
Yes.
I can put a metric there, and I know the strain will come with metric. So why didn't you couple the U with derivatives of the parameter?
So we could do that. Those are higher order terms in the Landau theory. So if you do the power counting, those are higher order. So they're less relevant than this particular coupling right here. And I mean, one way to think about this strain order parameter coupling, I could imagine embedding the strain into this coefficient of this quadratic term. So it's like it'd be like having a critical temperature that was strain dependent. And versions of that kind of model have been studied, long ago, kind of compressible spin models, for instance, compressible XY. This would be a compressible XY model. But there have been lots of compressible Ising models and compressible Heisenberg models, which have interesting anomalous features, which we've been pointed out, but none of which were ever observed.
Sorry, can I ask a
Yeah.
question?
Sure, what,
To go from the solid back to the, so if you set A1 to 0, and you're back to the fluid.
back to the fluid, yeah. that's
So
right.
what value does A1 need to take for it to be a solid, not a fluid?
Oh, we're just taking that as a phenomenological kind of parameter, so we're assuming that. That there is such a coupling and then kind of tracing through. The properties. Was that your question or?
Okay, so you say there is some value of, if A1 is bigger than some number, that is a solid, you just don't know the number.
I don't know the number, yeah, I mean, that's the nature of doing phenomenology. So I, you know, we. We
But
don't
aren't
necessarily,
you going to need to know if you have your super solid, you need to know that if that number is higher or lower than where you lose.
yeah,
Boston condensate.
we do, and we don't have a way of tracking that from first principles. I mean, in practice, you can imagine doing a numerical work. Just starting with the helium-helium interactions, kind of tracing that through. That's what we've just done the phenomenology here, saying if there are these two phases, they'd be coupled together. This is the coupling that's allowed by symmetry. And let's trace through what the consequences of that are for various kinds of thermodynamic properties, transport properties, and that sort of.
So remind me if this is true. So if I imagine taking your Landau Ginsburg sort of a theory and going within the solid phase, I want to study the transition of the onset of superfluidity. Well, supersolidity, but really just because your phase boundary, the vertical phase boundary is within the solid phase, I can just ask what happens this way.
Yeah.
So I remember at least compressible Ising models, the first consequence of that coupling is that the transition goes first order.
That is correct.
Is that also true for the XY order parameter?
It is not.
That's interesting. Okay, I didn't know that.
That's right. So, yeah, you're correct. I mean, that was early work. Was it by Michael Fisher?
I just don't know
No,
I remember it's not Halperin and.
Yeah, there was work in the early '70s on these.
So is it still an XY transition?
So it's in the, yeah, the claim is this, it's in the X, so this is a irrelevant operator.
I see. Okay.
So that the thermodynamic anomalies are the same for the supersolid in this
Mhm.
model as they would be for the superfluid. But as I like to say, the fact that something is irrelevant in the RG sense doesn't mean it's unimportant.
Sure. Well,
And-
you're not interested in the critical point, you're interested in the phase.
Yeah, and moreover, I mean, it's that kind of coupling which allows us to say the elastic moduli will pick up singularities that they inherit from the superfluid.
Yeah. Well, they're energy like singularities.
Yeah.
They're always allowed.
I'm gonna go through this quickly. So there's some interesting features in this model, which have also been observed in some of the Monte Carlo calculations, first principle calculations that a number of groups have done. And that has to do with the presence of various defects in the solid. And these are not the vacancies and interstitials that I talked about previously, but rather dislocations in the solid. So the dislocation you can visualize. This is a simple, what's called an edge dislocation, where you imagine taking a half plane of atoms and inserting it into your solid. And this defect is characterized by this vector here called the Berger's vector. There's an energy required to create such a dislocation. And we can actually try to calculate the properties of an edge dislocation in this super solid model by, again, we have a coupling between the lattice elasticity. We can put in the lattice model an edge dislocation and kind of trace through what that means for the superfluidity. And interestingly, what one finds is that these dislocations tend to promote superfluidity. So you could have a situation where the system might not be superfluid in the bulk, but there's a promotion of superfluidity near this dislocation near its core. And so you could have superfluid vortex, superfluid dislocation cores as well.
So what does that promotion, how does that promotion show up in the calculation? Like,
Well, okay, yeah, so right, so what one can do is you want to ask how that dislocation changes the effective TC.
Oh.
So you can do a linearized calculation to look at where how the instability has changed or shifted, and which we did. And there's some interesting, I would say, mathematical physics involved there. We can look at those shifts in the end. And again, there's also in parallel some Monte Carlo work on dislocations in helium-4 crystals that also indicated that there might be some superfluidity that's promoted by various defects in the crystal. So it's interesting.
I mean, I think the way I understand it is that, at least I heard this, David Hughes likes to talk about it as a commensurate, self-commensurate crystal. And if you have a line of dislocations like that, you're actually naturally deviating from half filling. And so you have a Luttinger liquid, at least that's what Anatoly and company found, that they can measure Luttinger exponents, and they're typically dilute bosons are superfluid, prone to superfluidity in one dimension. So those Luttinger liquids have Luttinger parameter.
Yeah.
That's superfluid.
All right, so I'm going to kind of fast forward to 2012. So this is the original this Nature paper by Kim and Chan entitled Probable Observation of a Supersolid Helium Phase, published in 2004. And this is another paper by Kim and Chan. Different Kim, same Chan, published in Physical Review Letters in 2012, Absence of Supersolidity in Solid Helium in Porous Biquark glass. So what happened over that 8-year period is there were a lot of really, I would say, careful experiments done by a number of groups, which refined the experimental techniques, that kind of refinements of the apparatus, improved torsional oscillators, improved measurement techniques. And with each improvement, the observed size of this non-classical rotational inertia effect became smaller and smaller. And eventually it appeared just to have gone away. So it's to some extent, that particular thread of at least experimental research more or less stopped after 2012. There have been some follow-up experiments in various other kinds of geometries, but it seemed like the conclusion was, well, maybe there wasn't any supersolidity there after all.
the New York Times did not follow.
I don't recall a New York Times article, although I did read about it, and it was maybe in Science or Nature, even though this is published in PRL. But yes, right. There's no Science Times did not cover it, as far as I'm aware. But over the last roughly 5 years, I would say there's been a revival of interest in the physics of supersolids, not in solid helium-4, but rather in cold atomic gases, and specifically in dipolar condensates. So these are bosons. So dysprosium-162, which has a fairly large magnetic dipole moment. These magnetic dipoles are aligned with a weak field and trapped in such a way that they're sort of quasi two-dimensional. The dipoles can repel And they form all kinds of different phases. So they can form kind of labyrinth phases, droplet phases, striped phases, and so on, which can be imaged directly by the experimentalists. And so here are some figures that I lifted from a PRX paper by Hirtkorn et al., where you can see the evolution of the density into these striped phases. And I want to give a shout out to Johannes Hoffman, who with the Willis Verger had developed a theory for a superfluid smectic. So a smectic being a layered system, looking at the physics of a layered Bose system, if you like. And I like to think of these dipolar gases as what I would call quantum ferrofluids. And so for those of you who don't know about ferrofluids, you should go ask Sriram, for instance, who's worked on this. A ferrofluid is a classical system which you have a collection of magnetic particles that are immersed in some background fluid, and they are designed in such a way that they don't glom together, I guess. And this magnetic fluid, it doesn't have a spontaneous magnetization, but it has a very large magnetic susceptibility. So you can easily, with the magnetic field, align the dipoles in this fluid, and they form all kinds of beautiful patterns and so on. So there's a great book by Rosenzweig on hydrodynamics of ferrofluids. Is that ferrohydrodynamics? So these are well known in the context of class. So ferrofluids are well known, well studied for classical systems. In fact, I was told by somebody that ferrofluids, this goes back to a discussion we had about applications, that they're used in braking systems, apparently.
Actually, they were invented to transfer jet fuel in space stations.
Okay.
Because without kind of transferring them physically, so you can use magnetic field to transfer the fuel. So immerse the ferroparticles into the fuel and shut it in, but that was kind of shut down because they kind of splatter it all over the place. But then, yeah, braking system and lubrication.
Yeah. Well, these ferrofluids, the classical ones, form all kinds of interesting patterns. They form stripes, they form bubble phases, and so on. And so I'm viewing these dipolar systems as like quantum ferrofluids, where these are bosons. So you have to put in the quantum statistics and all the interesting physics that is associated with the quantum mechanics of those systems. So it's a nice overview of this area in physics today by Landgren in March of 2022. And so I'm going to just zoom through the last 5 or so slides. Yes, yeah, guys, please.
Why, helium is not a supersolid, but these more complicated things are. What's the
difference?
Well, yeah, why do you think one is and the other isn't?
Yeah, I mean, partly it's the strong dipolar interactions that
Frustrated.
which give rise. I mean, it gives rise to, there's a competition. It gets back to some earlier work that I'm sure Vadim is familiar with on sort of mesophases and two-dimensional, say, electron systems, but you have this competition between long-range repulsive interactions, which would be the ferromagnetic interactions, and short-range attractive interactions of one type or another. And that competition on different length scales gets resolved at some intermediate scale, and the resolution is in the form of these various patterns, stripes, droplets, and so on. Now one big difference between these systems and the solid helium-4 is that, before in solid helium before, we were imagining a lattice, there was one particle per lattice site. Except if we had vacancies. I mean, here, the droplets and bubbles that form and that can themselves form a lattice. Each droplet has, thousands of atoms contained in it. So it's sort of a different setup. It's not the same as a commensurate crystal that we were used to for the helium-4. It's still a problem where you have broken translational symmetry due to the interactions, but it's not a commensurate crystal.
And why isn't this is probably a dumb question, why isn't the same experiment that was done for helium being done for this particular thing spin around?
Well, good question. So they're doing that. So that, I think those measurements of non-classical rotational inertia, they're looking for vortices right now. But I think it's possible to do some version of the NCRI measurements. Maybe Johannes knows better.
So, and how is it determined that these are supersolids without doing that experiment? Why?
Why are they super or?
So,
It's a totally different system. These are gases, and so you can basically look at them and see what's going on.
Yeah.
And helium,
It's all indirect.
yeah, helium is very inferred, where it's the usual sort of problem. This is like almost like pornography. You can look at it and see what it does.
the reason you can't do the same thing with helium is why?
Because I can be transparent. No, I mean, you have to set up an experiment to see superfluidity. These things, I guess you can see a central peak develop. You can basically let them go. There's the order parameter NFK, like in a BEC, NFK develops a delta function. So here they can just, presumably they can do time of flight.
They
and
time of
can-
flight and
time, they
look at
basically
phase
let go,
interference.
right, and then map out what.
Yeah.
The order parameter.
They can determine that these are phase coherence, so that there are those condensed. So just the opportunities for visualization and kind of directly seeing what's going on in these dipolar condensates is much richer than the kinds of tools that we have available to us for helium-4, which is, in this torsion cell at Kelvin, at 25 or 40 atmospheres, whatever it might be, where it's indirectly inferred whether or not it's becomes superfluid or supersonic.
But the Chester's ideas can be tested here more directly, right? So do you see in these experiments the role of vacancies? Like, for example, cold atomic gases, you can make the vacancies to go zero basically. You can remove the vacancies.
Yeah, I don't know if they've done that or not.
I mean, I think one of the issues is gonna be that there are very few atoms. There's probably like 1,000 atoms here, or there are 10 to the 5.
How do I see the difference between a Wigner crystal like phase, when you kind of rotate a BEC, you can develop crystalline phases, and a super solid? Because here, let's say if you somehow have the tool to remove all the vacancies,
Yeah.
you should go back to Penrose and Sarday, right?
Yeah, it's a different,
But
yeah,
are there any vacancies in this system?
well,
You can,
No, but you just answered your question. So all these dipolar things, sorry, I meant to like give a perspective, since you mentioned ferrofluids. If you take a bunch of dipoles and they form these macro domains. So what people call a crystal is kind of like if it had, if there's several atoms per unit cell, it's kind of like a mesocrystal, right? And it's kind of like, I feel like it's just sorry.
they're mesocrystal, they're mesoscale phases that develop.
Sure, but this is like so far away from the supposedly like fundamental question of liquid helium, where there's a crystal with one atom per unit cell.
Right, whereas the solid phase for these dipolar condensates would consist of, they can make these like in a quasi one-dimensional trap. You can get a quasi one-dimensional solid where the particle density gets modulated. But it's not one particle per site, but rather they're kind of clumps of particles. And I think probably the better model to understand this that I've been thinking about is in terms of, it's a bit like a Josephson junction array.
Right.
Where you get the clumps are like an island, and in the Josephson junction, then we get phase coherence, which is determined by Josephson coupling between adjacent islands. And so there's probably a different, but they still oscillate. So it's like a Josephson junction array with, it's a compressible Josephson junction array.
So I just have a question, is there any evidence, theory or experiment, this is two-dimensional supersolidity, or should I think of this as legitimately a one-dimensional?
They've done one-dimensional and two-dimensional as well. It's quasi two-dimensional, so they can make the third trap dimension narrow, but there is an issue. I was talking to Johannes about this recently. The dipole-dipole interaction is repulsive if the dipoles are parallel, but if you allow for them to sit on top of each other, then you change the sign of the interactions, and that will happen if it's not fully two-dimensional. So if there's some finite width in the third dimension, that actually modifies the effective a dipolar interaction between the atoms.
Yeah, but in one dimension, if you polarize them at an angle, you create all kinds of
You
weird
can do that as well.
interactions.
Exactly. You can take the applied field and you can tilt it and cant the spins and get other kinds of phases. All right, so, well, I was gonna go through hydrodynamics, kind of give a tutorial on hydrodynamics, but I'm gonna skip this. One of the things that I did 15 years ago with my PhD student, Chideok Yu, is to develop a hydrodynamic theory for supersolids, which had been done previously, but we wanted some kind of like an effective action to write down for a supersolid, and to then explore collective modes in the supersolid, but look at other excitations, including vortex excitations. So this is my kind of cartoon approach to how one develops a hydrodynamic theory for supersolids, but I'm not going to skip through much of this. This has to do with node counting and so on.
So just a very dumb question.
Yeah, please.
Isn't the whole point of a supersolid that there should be no fusion? So I don't understand the basic level what you mean by hydrodynamics, so the super part. The super.
Oh, yeah, so right, so I'm going to write down, so the idea, roughly speaking, is just like in a classical fluid, I want to look at conserved densities and write down the equations of continuity for those conserved densities, and also come up with thermodynamic relations that relate the different densities for the supersolid. And so this is my cartoon for just a simple fluid where we have five, in 3 dimensions, we have 5 conserved densities. We have energy, we have mass, and then 3 components of momentum. We get then 5 collective modes, 2 of which are propagating. So there's just sound modes, and then we have 3 diffusive modes. So I want to do the same kind of mode counting for a supersolid where this is for a superfluid. For superfluid, for instance, I now have an additional broken symmetry. I have to account for that in my equations of motion. Rather than 5 modes, I get 6 modes. And the 6 modes are the first sound modes, 2 of those, but I get 2 second sound modes as well. And those second sound modes are linear combinations of the superfluid motion and the entropy density, as it turns out. So they're often referred to as thermal waves in a superfluid. So I don't know, I mean,
Yeah.
so that, well, light scattering. So I wanted to then develop a similar kind of theory for supersolid, with just kind of looking at the conserved quantities, the broken symmetries. So conserved quantities, density, momentum density, and energy, and broken symmetries, which include translational symmetry. We did in 3 dimensions in 3 different directions, but also the gauge symmetry. And the question is, how do all these things conspire, come together, interact, and so on? And that's what the effective action will tell us. Our our theory basically reproduces work by Andreev and Lifshitz in 1969 on the hydrodynamics. But we're also able to do things such as look at correlation functions, possible light scattering, and so on. So our supersolid Lagrangian, well, there it is. It's a coupling between a phase degree of freedom for the superfluid, if you like, but also couples in lattice degrees of freedom, and the coupling between the superfluid and the lattice. Vn is the time derivative of the displacement vector for a lattice displacement. Gradient of phi is the superfluid velocity. So there's a velocity coupling in supersolid, which gives rise to all kind of the rich physics that exists in these systems. So zooming past that. And so as an example, what we can do, we can calculate a density correlation function, which is something that might be observed in light scattering. And we can look at things like here's over here, that the green curve, which you can barely see, is the central Rayleigh peak that would exist in a regular solid. But as we go into the supersolid phase, that Rayleigh peak gets split into two Brillouin peaks here on the side. So they're propagating modes, just like you would see propagating modes and light scattering for a simple classical fluid. Here's our action. Let's skip ahead. And then, as I mentioned, one of the things that we can do with our effective actions, we can look at, say, vortices in a supersolid. And we have a way of looking at the vortex dynamics in a fairly controlled fashion, where we can put a vortice into a vortex into a supersolid. We can put a dislocation into the solid part, look at how they move around, but also how they might choose to interact. And well, there you go. There's the effective action. And for vortices, and the idea is, if you have a vortex in any kind of compressible medium, if the order parameter couples to that medium, as the vortex moves around, it creates a series of waves that propagate and interact with the second vortex. So there's sort of this Lorentz invariant interaction between two vortices in a supersolid. The superfluid, you get the same thing, but the interaction will only be mediated by the Goldstone modes in the superfluid. Here we have that interaction mediated both by the Goldstone modes in the superfluid, but also by the elastic waves in the solid. So it's kind of a richer vortex dynamics that exists here. And oops, did I do it?
How do you implant this vortex into your action? Like you put it in a bag, like a source term?
Yeah, we put it in as a source term. So you break up the phase into a smooth longitudinal piece, and then a transverse piece, which has the vortex encoded in it. And that's where there's something on here. Anyway,
I'm actually confused about
that's the
something.
vortex degree of
Can I
freedom.
just ask, I wasn't, fortunately, I wasn't paying attention. And also you breezed past the Lagrangian. This, should I take this as a zero temperature action or finite
Yeah, you
temperature?
could take this as zero temperature, although when we do the hydrodynamic, well, we derive the action. From that, we can get the dissipationless hydrodynamic equations. But we can also go back in and put in the dissipative terms as well. That's a fairly complicated, so that would
But
be.
that's actually potentially more relevant, because like, for example, I had a question I was trying to answer.
Yeah.
Well, no, I was trying to answer the
Yeah,
question while we
okay.
were talking these other things.
Yes.
One question is that suppose tomorrow somebody figures out how to get supersolid back in New York Times.
Yes, right.
Okay, and the phase diagram is going to be similar to that, but proper supersolid, not these dipolar
Yeah.
sort of a simple cases. Then one intuitive question, it's a yes or no question, you know, so if you're in a solid, we know that. Topological defects have a really hard time moving around, there's, you know, they're very collective. So if you all of a sudden go from a solid to a super solid. Do we expect a qualitative change in the mobility of topological defect? Because ultimately, for you to be able to find a stoichiometric solid, it's better to have mobile topological defects. So
Right.
from this theory, do you expect that, say, dislocations, disclinations of a solid? Because you can set up experiments to estimate their mobility, right?
Yes.
Do you expect that they'll become more mobile or less mobile?
Yeah, so,
And I don't know how to do that calculation in
Right.
the zero temperature theory. I want like
yeah,
stochastic theory.
so we can set it up. I mean, honestly, from what I know now, I forgot to reference this, but we have a preprint out on the archive. Posted about 2 weeks ago on the vortex dynamics for the supersolids. So if you're interested, there's a
Okay.
preprint by you and Dorsey on the archive.
But this is in a zero temperature theory or fine?
It's the zero temperature,
Okay.
just looking at the vortex dynamics. And one of the things we can do is we can get an effective mass for a vortex, which comes about from basically, as the vortex moves along, it generates these sound modes. And there's an effective, which can act back on itself. So there's a self-interaction, if you like, which gives rise to an effective inertia for the vortex. So we can calculate what that looks like, you know, for a super solid, which would be different than a super fluid. So there's an effect there. It's not very dramatic. And if we did the same thing for dislocations, I think at least in this model, I don't think we would find anything very dramatic. We would find maybe an effective change, a change in the effective mass of a dislocation.
I mean, that makes sense.
But it's all within this framework. Now, is there some physics we're leaving out? Probably.
Okay.
Yeah. Okay, so, yeah, so as I mentioned, we can get an effective action for the vortices by themselves, which include an effective mass, which happens to be frequency dependent. So it's a little unusual, but people have done calculations for effective masses for vortices and superfluids, find something very similar. And it's no different here, but because we're coupling to additional degrees of freedom, that mass brings in coupling to both the longitudinal and transverse phonons that would exist in the solid.
And I think of this as a memory effect.
It's a memory effect, exactly. That's exactly what it is. Yeah. All right. So just to kind of summarize, supersolids are still interesting, at least to me. And you know, it's a case where you have competing orders, in some case subtle, you know, in this case between off diagonal long range order and crystallinity, solid order. I think the conclusion right now is helium-4 probably doesn't have a supersolid phase. But dipolar atomic gases do seem to have supersolid phases. They form these smectic phases, strike phases, bubbles, and so on. And I alluded to the fact that they're now doing experiments where they can, these are the dipolar atomic gases, they can rotate them so they can put vortices in as well. So there's the possibility of looking at vortex dynamics in these supersolid models too, which is kind of cool. And I think, you know, looking at effective field theories, hydrodynamic approaches gives you a lot of insight. Of course, it's not first principles microscopic. There are a lot of phenomenological parameters we have to put in. That's the nature of hydrodynamics. But I think we can capture certain interesting features, including, you know, the collective modes that exist in a supersolid, which are something that might be measured, but they're measurable for the experimentalists doing the experiments in the dipolar atomic gases. And that's it. So thank you.
All right. So there was one question on Zoom.
Yes.
Which was pretty early on. I'm not sure, it's probably irrelevant by now. It's something about whether there is an effect from symmetry on BC. In other words, how does interstitials affect the formation of BC? My understanding is that it's either or interstitials or vacancies, both of them are beneficial, is that right?
I think that's correct.
Right.
Usually we talk about vacancies.
Yeah, why?
Well,
Yeah, I guess maybe that's that's a good segue.
why?
Why not interstitials? Is there a mass kind of like, because in Andreev and Lifshitz, they estimated the mass and it was just too heavy.
Yeah, I don't know the answer to that. They certainly have different properties, but the whole framework is developed in terms of there being a vacancy band, which Andrei Lifshitz, I think, referred to as defectons.
Right.
And it's that band, which is presumably dilute, which forms the superfluid, if you like, so.
Okay, are there any quick burning questions that cannot be asked over lunch?
I have a question.
Yes.
Please.
Hi, Alan. Good to hear your talk. So, do I understand correctly that in your description, in your general theory, there is no difference between, let's say, actual supersolid of the same component, or if you consider two-component supersolid? For example, one component forms solid and another one forms liquid. So is there an essential difference, or I'm missing something?
So are you asking whether or not there are two different atomic species that would?
No, let's say you consider not helium-4 or let's say proper supersolid of one component, the same component forming solid and liquid. Let's say two-component material, one component forms a solid and another one, it's like a metal, but let's say if you replace electrons by bosons and remove, let's say, electromagnetic interaction, would there be some effect which allows you to distinguish in your theory between two options?
Yeah, but some of the things that happen in building.
I've never thought about that, so let me just.
Okay.
So. That's worth, so I don't know the answer. Worth exploring, I guess. And certainly, I mean, the dipolar atomic gases, they could also set up condensates with two atomic species. I mean, maybe that would be one as well. So I don't have a good answer to your question.
Okay. Okay, fair enough. Thanks.
Forgot to thank Alan. We closed. All right, let's reconvene 12:50 or something like this. Thanks, Alan. Sorry. Just wanted to stay on schedule.
Yeah, of course.
That was good. I have wait, let me pause the recording stuff.
Let me unplug.